talk about symmetry in functions. So we're going to talk about 4 different types of symmetry. The first one is called an even function, and that is a function that is symmetric about the y-axis. So here is an example. This function here, there's the y-axis, and that is a line of symmetry for this function. Okay, so that's a type of function with symmetry about the y-axis. It's got a special name called an even function. So if you are just given an equation and you want to know, will a function with this equation be an even function? Will it have symmetry about the y-axis? The test is f of the opposite of x will equal opposite, or f, I'm sorry, let me start that over. F of the opposite of x will equal f of x. And that f of x, that is the original function. Okay, and the reason this works is that for every x value on this function, the opposite x value should exist as well. So f of the opposite of x for this function is negative, and then opposite of x, because whatever this x value is, its opposite should also exist if it is an even function. Okay? And f of x, the original function was negative x squared minus 3. Mathematically, are these two exactly the same? And if they are, then there is symmetry about the y-axis. So negative x, when we've got that negative x in parentheses, to the second power, say that's a 4. Negative 4 squared is 16. Positive 4 squared is also 16. So what's in the parentheses here, negative x, if I square it, that is exactly the same as a regular positive x squared. Still got this negative outside. And these are the same mathematically. So yes, this does have symmetry about the y-axis. So this right here, this one right here, is an even function. Okay, is this an even function? Okay, so this time it's y equals, but that's fine. So we've got y equals the absolute value of the opposite of x plus 7. Okay? Now, for any number, so say negative 3, its absolute value is exactly the same as the absolute value of positive 3. So the absolute value of negative x is the same as the absolute value of positive x. And that is exactly the same as that. So this is also an even function. Okay, what this would actually be is a V shape up here, and it is symmetric about the y-axis. Okay, the next type of symmetry is symmetry about the origin. This is rotational symmetry about the origin, and if that exists, then you're looking at an odd function. This here is an odd function. So there's the origin. I can rotate this 180 degrees and it will fall right back on itself. The test for that type of symmetry is f of the opposite of x should be exactly the same as the opposite of f of x. So for this function right here, I have to check what f of the opposite of x equals. So f of the opposite of x is negative x to the 7th power minus 2 times negative x. Okay? Now, negative x to the 7th power, that's an odd power. That will not cancel that negative. So it's going to stay negative x to the 7th power. Okay? And that would actually be the same, this negative x to the 7th power. Let me finish this line and then we'll talk about that. So negative 2 times negative x is plus 2x. negative x to the 7th power is exactly the same as the opposite of x to the 7th power. Okay? So that's as simplified as I can get. Now, the opposite of f of x is negative, or the opposite of, this entire function. So I distribute that negative, and I get the opposite of x to the 7th plus 2x, and those are the same. So this is an odd function. It does have symmetry about the origin. Okay, we'll test this one to see if it's an odd function. F of the opposite of x is 2 over negative x. The opposite of f of x is negative 2 over x. When there is one negative inside of a fraction, it does not matter if it's in the top, the bottom, or in front. It all means the same thing. So this is a negative fraction. And this, I can put this negative top, bottom, or in front. This is a negative fraction. They are the same. So f of opposite of x and opposite of f of x are the same. So this does have symmetry with respect to the origin. So it is an odd function. All right, some other symmetries. We can have lines that are symmetric about the x-axis. Okay, and a line like that, or not a line, but a graph like that could look maybe like this. Parabola turns sideways, that would not be a function, but as a graph that has symmetry about the x-axis. For every y value on this graph, that opposite y value exists. So I should be able to turn any y into the opposite of y and get the original equation back out. Symmetric about y equals x. So here's y equals x. You could have a graph that maybe looks like this. Okay, so that's got symmetry about y equals x. If y equals x, then x equals y, so every y and x can be substituted with the opposite. So every x can become a y, every y can become an x, and we'll still be able to simplify it mathematically to the same original equation. Symmetry about y equals the opposite of x, so that's symmetry over that line. Well, if y equals the opposite of x, then x equals the opposite of y. So I should be able to take every x and y and replace them with a negative y and negative x and get the same original equation. So we're going to run some tests on some graphs without even seeing the graph. xy equals -4. Okay, so I want to determine, is it symmetric about the x-axis? If it is symmetric about the x-axis, then that's going to look like this. Every y value, its opposite will also exist. So I'm going to take every x and leave it x, and take every y and make it the opposite of y, and see if it mathematically equals the same as the original function. So x times the opposite of y equals -4. Okay, so for testing the x-axis, it's the opposite of y. X times -y is -xy, and that does not equal the original function. So there is no symmetry about the x-axis. How about symmetry about the y-axis? If there's symmetry about the y-axis, then every x that exists, its opposite will also exist. So I'm going to change all of my x's to the opposite sign. So I have an x here that's positive. I'm going to change that to a -x and see if I can simplify it to match the original equation. Okay, so I get -xy when I multiply these equals negative 4. By the way, if I want to make this a positive, I can, and to make it match that original. But when I do that, I'm dividing both sides by negative 1, and I get xy equals 4. Here I can do the same, xy equals 4, having divided both sides by negative 1. And now I've got that xy for both of these, but I've got to get the other side to equal the same thing as the original, and it doesn't. So it equals positive 4, not negative 4. Okay, so either one of these lines here does not match that original. So it is not symmetric about the y-axis. Next is symmetry about y equals x. If y equals x, then x equals y, so every x and y can get replaced with a y and an x, respectively. So this x times y, I'm going to replace that x with a y, and I'm going to replace that y with an x, and see if I can mathematically make it equal the same as the original. Okay, so multiplication is commutative, so y times x is the same as x times y. And that matches the original equation. This graph will have symmetry about y equals x. And then test for y equals negative x. Well, if y equals negative x, then every y value can get replaced with a negative x. And if this is true, then x equals negative y, so every x value can get replaced with a negative y. So my x becomes negative y, my y becomes negative x, and I have to see if I can mathematically make that equal the original equation. Negative y times negative x is the same as y times x. Okay, negative times negative is positive. And y times x is the same as x times y. And mathematically, I was able to make it match the original. There is symmetry about y equals negative x. Okay, we're going to do the same tests for x cubed plus y squared equals 12. So checking for symmetry about the x-axis. For x-axis, we check the opposite of y. So x cubed plus the opposite of y squared equals 12. If I square a negative, it becomes a positive. So the opposite of y squared, or negative y squared, is the same as positive y squared. And mathematically, I was just able to make that match the original equation. This does have symmetry about the x-axis. Symmetry about the y-axis. For that, I put in the opposite of x. So negative x cubed plus y squared equals 12. This has an odd power. An odd power does not cancel out a negative, so negative x cubed is exactly the same as the opposite of x cubed. Everything on the right side matches the original, but not everything on the left side does. So once I've got one side to match the original, I check and see, does the other side match? And it does not, so there is not symmetry about the y-axis. Symmetry about y equals x. So this is where I switch the x and the y. Y cubed plus x squared equals 12. Okay, so I've switched the x and the y. Now, mathematically, can I make them match the original? I can turn this around because addition is commutative. I can do x squared plus y cubed equals 12. But there's no way I can change those powers back to match the original. So there is no symmetry about y equals x. And for y equals negative x, I switch the variables and give them opposite signs. So the opposite of y squared plus the opposite of x, that's the opposite of y cubed plus the opposite of x squared equals 12. So I've switched the variables. The powers stay right where they were, but I switched the variables and negated both of them. Now I have to see if I can make it match the original. So negative y cubed is the same as the opposite of y cubed. That odd power does not cancel the negative. Here's an even power. It does cancel the negative, so that's the same as positive x squared. Okay, so now I can put that x squared in front, minus y cubed. I've done as much as I can. My signs aren't matching the original. My exponents aren't matching the original. There is no symmetry about y equals negative x. And last, determine for each graph whether it is symmetric about the origin, x-axis, y-axis, y equals x, y equals negative x, or none of those. So this one right here does not have a line of symmetry, but I could rotate it 180 degrees about the origin, and it would fall right back onto itself. So I would say this has symmetry about the origin. And don't forget that has a special name that we had on the first page. That is called an odd function if it has symmetry about the origin. This one right here, it looks like I've got a line of symmetry right there, and that is the x-axis, so this has symmetry about the x-axis. This one, I've got a line of symmetry there. That's symmetry about y equals x. And for this one, I've got symmetry right there. So there's my two parts of the graph. I've got symmetry there. That is symmetry about the y-axis. And that one also had a special name. That one is called an even function.